Hi students, and welcome to HSC Chemistry and the Acidic Environment video series. In this particular video we're going to be looking at the ionization of acids. Now we've said a couple of things. Firstly, that the strength of an acid is related to its degree of ionization. Now that also depends on the number of H+ ions that are available as a consequence of the ionization process. So we can classify acids also on the basis of the number of protons which they liberate in solution. So monoprotic will donate one proton, one H+ ion. And so one example of a monoprotic acid is hydrochloric acid. And remember now when we're writing our ionization equations, we are going to be writing the hydronium ion as the source of the just remove that, H3O plus aqueous and the Cl- ion. So remember that we're actually making our H+ ion to be the hydronium ion, the form of the hydronium ion, when we're looking at the ionization. Diprotic acids can donate 2 protons, and sulfuric acid is an example of this. Now, the important thing about the ionization of sulfuric acid is when we ionize sulfuric acid into a solution of into water, we have an H3O plus ion and an HSO4 minus ion. Now, obviously, these are both aqueous. And this one goes to completion. The second step in this particular ionization, plus water, also lies a long way to the right, but sometimes we don't entirely get the full ionization. So it is possible that we may have a very small amount of this particular ion that remains in the solution and not quite the full amount of these two. When you add these two equations together, these two should cancel out, and that will give you 2 of these and 2 of these. But just be aware of the fact that sometimes, even when we're talking about these strong acids, a diprotic acid, we're going to have a look at the nature of this particular substance in a subsequent video. And sometimes they don't always completely go through both full steps. Triprotics can therefore be even more of a complication, tri meaning 3 and phosphoric acid. And so when we're looking at phosphoric acid, if we want to go through the steps of ionization for phosphoric acid, then we're going to have quite a series of them. So an H3O plus here, H2PO4 minus, aqueous. The second ionization is H2PO4 minus plus H2O, liquid, and that again will leave a small equilibrium arrow there, mostly going to the right, H3O plus aqueous and HPO4 2 minus aqueous. And then the third stage is this HPO4 2 minus aqueous, again reacting with a water molecule in an equilibrium to form H3O plus aqueous and PO4 3 minus aqueous. Now, when we're looking at our cancellations, if we add all of these together, then we've got a cancellation here and here. We've also got a cancellation here and here. 2 things are on the same side of the equation. And so as a consequence of that, 3 water molecules will produce 3 hydronium ions and the phosphate ion. And just be aware that some of these processes do not go all the way to completion, but we often simplify them by assuming that they do. The important points then are that strong acids will always ionize to completion. They will be single directional arrows, but weak acids set up an equilibrium in solution, so therefore that equilibrium can go both ways. The ionization of acetic acid we've looked at before. CH3COOH is the formula for acetic acid, and when it's in water, the hydronium ion will form, but we'll also have a CH3COO minus ion, and both of these are aqueous. Now the problem is, because this is an equilibrium, we don't use the single directional arrow, we use our equilibrium arrow. So I shall replace that with an equilibrium arrow. Now the other thing that we want to do is we want to see the degree to which these solutions or these acids will ionize. So sometimes they will go a long way to the right and only a small amount of the molecule will remain. Other occasions they'll only go a small amount to the right and they'll basically remain positioned to the left. So the equilibrium position will either lie on the left-hand side or on the right-hand side. So this is lots of product, and this is lots of reactant. To give you a better understanding of that, let's have a look at a specific example. Degree of ionization can be calculated by looking at the concentration and the pH. In this situation, the concentration is equal to 0.1 moles per litre, but the pH is equal to 2.9. So we said before, concentration of H plus ions could be worked out by saying this is the same as 10 to the minus 2.9. This gives us an actual value of 0.00126 basically, and so on. Now the problem is that this concentration is a long way. 0.00126 is a lot less than 0.1, and in fact when we calculate it as a percentage, it works out to being 1.26%. So only 1.26% of the CH3COOH has been ionized. So effectively we have 98.74% of this molecule and only a 1.26% of the H plus ion. So that gives us some idea of the degree of ionization by a comparison between the starting concentration and the pH. Thanks for watching.